Welcome, differential calculus. So we had these lessons in differential calculus, and we will review important points. So the first lesson was fundamentals of derivatives, and we learned that the, if you integrated the derivative of the function, you'll get the original function. Basically, that's the derivative of the function, and then that's the integral of the derivative of the function, then you get the original function. So I have a function here, I could differentiate it once, could find the second derivative, I could find like the third derivative of the function. If I integrated that third derivative of the function, what will I get? I'll get my original function, which is the second derivative. If I integrated the second derivative of my function, what will I get? I will get my original function, which is first derivative. And if I integrated my first derivative, what will I get? I will get like my original function here. So that's like differentiation, and that's integration. So that's something you should. It's called the fundamental theorem of calculus. And we've seen that from this fundamental theorem of calculus, everything we do, like everything we in engineering, we do it, it's related either to the conservation of mass, conservation of energy, and conservation of momentum. And we have seen how this relates to the fundamental theorem of calculus, this conservation laws. Yeah. So we had some derivative rules like the power rule. So the power rule, like you have x to the power n, you bring this down and you subtract 1 from it. You have like the chain rule, you have the product rule, and you have the quotient rule. I wouldn't go through the details of this, you can just read them and you have practiced a lot already. Then you have also derivative of commonly used function like a to the power x, that's a to the power x ln x. Logarithmic function and trigonometric function. For your exam, I highly recommend that you will have something like this, yeah? You print something like this, just like even like just have it handy, like even print it, not on your computer because you don't want to waste time like searching here and there. Just one paper to print, yeah? And that would be like very handy for you in the exam. If you need me to print it for you, just let me know. Email me. Yeah. Tell me I don't have a printer. Could you please like print this for me? I will print it and bring it for you in the exam with me. Yeah. So just let me know. Okay. But it's very handy. That's for like derivative and integrals. Yeah. Let's go back here. Uh, we did some practice, so I like go like the exam will have a lot of these types of questions because this is again very basic, very fundamental. You are a civil and environmental engineer, and that's something you should just know by heart, yeah, just as an engineer, yeah. So for example, like you have something like this, when you have something like this, you would immediately see that you can use the product rule. So that would be like the first function times the derivative of the second function plus your second function plus the derivative of this function. Then when you see something like this, see something to the power 4, this looks like the power rule, but you have something inside. This is not to the power x, this is to the power something, like let's call z or n or whatever. Yes, this is something. So you need to know that you need to use the chain rule. So basically, like you use it, like you take the derivative of this guy, then you apply the power rule. So that's what we did here. Yeah, like so you apply the power rule, like you assume that this is x. So that would be you apply the power rule. So that would be 4, and you subtract 1 here, you get 3, and then you take the derivative of this guy, yeah? Uh, uh, and the derivative of this guy, that would be like 2x plus 8, yeah? And then you multiply. And then, so here, like this problem is a very good problem because it shows you like how to apply like the power rule, the chain rule, and the product rule. So try to do this, try to, like if you understand this, that's basically all you need to understand here. We also looked for like taking like the first, second, and this is like the first derivative of the function. This is the second derivative of the function. Yeah, so you should also be able to do this. Yeah, like take the first and second derivative, and like this is velocity, for example, and then if you take the derivative of velocity, you get acceleration. Okay. You have like there is a lot of problems that you can practice. So here, for example, like this problem, you can either solve it with the chain rule or the product rule. So try to do it with both. This is a good practice for you. Yeah. So with the uh, chain rule, you solve it in this way. The product rule, you just like multiply this by this and you solve it in this way. So that's a good practice. Yeah. Like if you understand this, then you understand a lot. So I provided for you a lot of practice problems, so try to do them. Yeah, like once if you can do them, then you will get the full mark in the exam. That will be a lot of question you will have in the exam will be similar to this, and if you can do this, then that's like these are easy points really in the exam. Yeah, so you can here for you here. I mean, I'm not gonna go through this like one by one, but try to do something like this. Here, like try to do something like this. I'm showing you like the chain rule. Like if you don't understand that chain rule, like here are the steps of the chain rule, so you can like look at it in details. If you don't understand the steps of the quotient rule, like here I'm putting the steps for like some of the practice problem, or I think this is a homework problem. That's for your homework problem. Like I'm showing you the steps, that's for your homework problem also. I'm showing you the steps, yeah. So try to solve this and try to see if you can do this. And try to do it quickly because remember the exam have like a certain number of questions and a limited amount of time. So you should be able to also do it fast. Yeah. So try to practice. The only way to do this problem is practice. Like if you can do what you see here in the practice problem, means that you will get the full mark in the exam. We also looked at the derivative tests. So derivative tests, what you need to understand, like you have a function. Yeah. In that case, that's like just 1D function. Real life optimization problem could be not just 1D, it could be like 20 dimensional or 40 or 50. Yeah, I solved an optimization problem, for example, with 80 dimensions. Yeah, but here just for doing this for one dimension just to illustrate the concept. So what concepts do I want you to learn? The main concepts that I want you to learn is that there is something called like a global maximum and global minimum, and similarly local maximum and local minimum. So the global maximum, that is the maximum point in the whole interval of your function. So in that case, what is the maximum point? So like you see here, I start from here, I go all here, 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 here. This is like, is this a global maximum? No, this is a local maximum. And then I go down and then this is like a global maximum. So this is a global maximum, yeah. What is the global minimum? So the global minimum is this guy. Yeah. And how to solve these types of problems? So the first thing to solve these types of problem, you find all the local minimum and local maximum. So here in that case, like I have this local minimum and I have this local minimum. Yeah. And then out of these two local minimum, I could also have my endpoints. So that my endpoints could be also like minimum. Yeah. So basically, I evaluate my endpoints. I evaluate this local minimum. I evaluate this local minimum. I evaluate this local minimum, and the global minimum would be this guy here because that is the lowest point out of like this guy, out of this guy, out of this guy, out of this guy. This is the minimum point. So that is my minimum value of y, which would be at x is equal to whatever, like 2.1 or something like this. Yeah. And that's the maximum value of y, which is b equal to 3 or something at like a value of 2 point something. Yeah. So that's basically like what you need to do. And to find like global maximum, global minimum, and the inflection point of a function, like there's a process. So you need to like find the critical point, and like at the critical point, so the critical point, that's like when your rate of a change is equal to 0. So like you see here, like I evaluate my derivative. So here I have like my gradient is positive, positive, positive. Here my gradient is negative. The rate of a change is 0, and here is negative. Yeah. So I find like similarly for an inflection point. So how to do this? You find like all the critical point. Like what do I mean by critical points? These are when the rate of a change is 0. Yeah. So, so I find the first derivative and I equal it to 0, and then I find like all the points. Here I have like x is equal to 0 and x is equal to 1. Then you calculate the second derivative. So if the second derivative, if it is like less than 0, that's like a maximum point. If it is like greater than 0, that is a minimum point. If it is equal to 0, that's an inflection point. So here I evaluate this. So this is like the second derivative, the rate of a change of the rate of a change. So if here, if this is like, let's say like this is like going up, like, so if this is like negative, yeah, the second rate of a change is negative, then that would be like a maximum point. Yeah. And that's because I was here like moving up, and then I started to move down. So like you're going up, so like you see you're going up here, and then you're going down here. So the second, you'll be curving down, so the second derivative will be negative, and that's the would tell you like a maximum point. Versus here, like an inflection point, I was like, I'm flat, and then after the inflection point, I'm also flat. So the second rate of change, I'm not either curving up or curving down. So the second rate of the second derivative, the rate of a change of the rate of a change, or the second derivative of 0, versus the minimum point, I was like going up, and then I was going down and then curving up. So because I'm curving up, like I have like the second derivative, or the rate of a change of the rate of a change is positive because I'm curving up. So that's like would be like a local minimum. Yeah. So, and then you just follow this step. So here is like an example. Like I'm not gonna go through these details, but like by just looking at this, yeah. Where is the global, how many local minimum we have? We have one local minimum. How many local maximum we have? We have one local maximum. What is the global minimum? The global minimum is not like this guy, but it is an endpoint in that case. So that's the global minimum. What is the global maximum? The global maximum is not this one, not this one. It is like this guy here. Yeah. And here I have like an inflection point here. So here, like you see, this is global maximum, endpoint, global minimum, minimum, and endpoint. Yeah. So you just like look at these detail, like you can pause the video, look at these detail, make sure you can solve these problems. So that's a good practice. I think your exam will have something like this. We also saw how to formulate like an optimization problem, like simple optimization problem. So if you're giving something like this, then how you can put make like your objective function. So that's like your objective function here, and then so that's my objective function, like the cost as the cost of the top and the bottom and the cost of the size, for example, and that is subject to this condition. And then we will see like again, like you follow the same process. So that's your objective function. You find the first derivative, uh, and then from the first derivative you would try to locate like as extreme point, like the local maximum and local minimum, for example, and then you evaluate this extreme point like to. So here I was able to find like 1 point, solving for r, and then like if I have r, for example, I can substitute here and solve for h, and then I can solve for the cost, and then evaluate this. If I calculated the second derivative, this is obvious that this is larger than 0, confirming that this is a minimum point. So here I was able to find the minimum cost for this fence, for example. Yeah. So should be able to do these things also. And you have like some practice problem and your homework problem. So try to solve these things. We also looked at multivariable derivatives. So multivariable derivative, we look at parametric equations. So the parametric equation, I have like a function like with multivariables. It's a function of x and a function of y. So what we can do is that we can express the derivative in terms of the parameter, let's say s, which governs the behavior of both x and y. So that's called like a parametric equation. So for example, a curve is defined by a parametric equation with respect to s. So you have like x, that's like as a function of s, and y as a function of s. And that's how I could relate x and y. And then how to find like dy by dx, that basically would be the dy by ds, like this intermediate parameter, and dx by ds. Because like if ds go away, then you'll get dy by dx. Yeah. So we've looked at this, like you can do some practice again here. This is like a parametric equation, and you can solve something like this. In the final exam, like for example, sine over cosine is equal to tan. This is general knowledge from trigonometry, but I don't expect you to, because like we didn't cover trigonometry, we didn't review trigonometry. So in the final exam, for example, it would be multiple choice, so you will not choose like tan x. I will give you something like negative sine over cosine theta, for example. I'm not going to give you this one because I know that we might like forget like these trigonometric like relationship. Yeah, and we didn't review it in this class, so you don't need to worry about this. Yeah, but the final, so in your multiple choice you will be giving something like this. Okay. uh, we also looked at the partial derivative. And the partial derivative like this could be found with respect to one independent variable, while I treat all the other variable as constant. So for example, I have this equation of like sphere, for example, and I want to find like so this is, I mean, excuse my bad drawing, but this should be like part of like a sphere here. And what I want to do, so this is like my x and y, and this is my z here. And then if I can find like a plan of constant y, and then at this plan of constant y I will have like this line here, which like you see this line here. So now y is constant, like I'm not changing y like at this given y. And then I find the slope of delta z with respect to delta x, and I can find the rate of a change at like this curve here at a constant y, like giving that y is constant. So here, this like my equations, that's like as equation of the sphere x squared plus y squared plus z squared, that's equal to 9. That would be like the uh, diameter of like the sphere, yeah, and or the radius, like this is diameter, yeah, and yeah, this is the diameter. And then you can find the z is equal to the square root of this, and then like for a constant y, and now I can find partial derivative. So partial z, partial x, and then is equal to this is to the power of 1 over 2. This guy, I can solve this. So this is like I can easily like solve this. So that's a good practice again for you. Like try to solve this using the chain rule. And when you solve this, this is constant, this is constant. So you only get 2x, and then this will go away with this 2. So you get something like this. So try to solve this. And then if I want to evaluate, find the slope at a point. Like, so if I want to evaluate the slope at this point, you just like evaluate your partial derivative at this point, and that slope here would be like negative half, for example. Yeah. So this is some practice problem. And again, be careful. Like here, partial z g with respect to partial v, that would be different than partial v with respect to partial z. Yeah. So be careful, like what you are doing or what you are solving for. So here, that's like one practice problem. Like if you can do like this practice problem, like try to do it, and that should be easy for like the exam. Like so, like here's a practice problem. You go through your lecture notes, you will find like more practice problems, and remember, like there are slides. So like in addition to the video, if you don't want to look at the video, you can just look at the slides. Like open like at the beginning of each module, I put all the slide, I put all the materials, the Excel sheets, the Python file, everything in just like one page at the beginning of each module. So go there and you will find like the full slides, which you will find like more homework practice problem and exercise problem for you to solve. We also looked at the total derivative, partial derivative, and parametric equation and like chain rule, like how you can apply all this together. And we've seen that like through the chain rule, you can express like the total derivative in terms of partial derivative. So that's we've seen that this is like through the chain rule, and that is could be also useful for solving some problems. So here practice like total derivative, partial derivative, and the parametric equation. So I'm giving you here h as a function of time, for example, and then I'm giving you temperature as a function of h and x, like some distance, and I'm telling you find uh, temperature, how temperature is not how temperature is changing with height, like elevation and distance, like how far you go, but how temperature is changing in time. Like somebody is walking up the hill like at 1.5 hours, what would be the temperature? Like he's climbing a mountain or whatever. At that time, what would be the temperature? So you can track his temperature as he moves up in elevation and distance, things like that. So here you can like use this total derivative, you can express it as partial derivative, and that you can solve this problem. So yeah, so that's also like try to read this problem and try be also a good exercise. Remember, like your exam, like you have to solve the problem, but the final answer would be like multiple choice. So I will just put this problem. The problem will be the same. Yeah, if I'm giving you this problem, I'm don't know if you have a problem like this in the exam. You may or may not, but it will be the same problem, but and you will be giving the four answers to choose from. So the answer, is it negative 0.02, or is it 0.02, or is it zero point zero 0.05, for example, or is it like zero point 0.1? Yeah, and then you have to choose the correct answer. Yeah, so the exam, same type of question, but the format would be slightly different, because in the exam you be all MCQ. You have to either MCQ or like select all the correct answer, and make sure to select all the correct answer. Like make sure to read the problem very carefully. It's just telling you select one correct answer, you select one correct answer. If it's telling you select all the correct answers, then you select all the correct answers in order not to lose points. So, and there could be also true and false. Like I could give you like the answer of this problem, is this true or false? Yeah, that could be also. So the exam would be MCQ, true or false, and select all the correct answers. That's the exam. Yeah. We looked also at implicit differentiation, which is like the easiest of all like these guys, and that's basically based on like this chain rule of like total derivative, but like you equate this to zero. Yeah. So when you equate this to zero, then you will get like the total derivative of dx over dy, that's equal to negative partial derivative. And this is like, if you are wondering like how did you go from here to here, I'm just showing you the steps. So that's one of the students, she was confused, like how did I go from here to here? So these are the steps. So I think this you can also find this in your lecture note. Yeah, how to get from here to here. But anyway, so you have this equation, and this is like very easy for solving problem, because like remember, like this guy here, we used like we solved it previously using the chain rule, but if you solve it this was partial derivative, and in the FE exam you're going to get at least one of these problems. And something that looks like this, and then, or I don't know if you will get it or not, but like I seen it almost in all the books that I consulted. So like these types of problems, so you may get it, yeah. I don't know, but you might get it, yeah. So like, and you get like a problem like this, it's just like it's much easier to just solve it with instead of like using the chain rule here, just like use partial derivative, yeah. And then you get something like this, okay. So the summary, total derivative represents the rate of a change of a function with respect to one variable, considering all indirect changes through other variables. While partial derivative represents the rate of a change of a function with respect to one variable while keeping the other variable constant. So here I'm considering all variable here. I'm just considering one variable and keeping all the other constant. Yeah. Uh, so total derivative accounts for all passive variation while the partial derivative isolates the effect of a single variable. Okay. We also looked at the vector calculus. We looked at three things. We looked at the gradient, divergence, and curl. We looked at first like a vector. So a vector could be presented like in this way, like ijk, or it could be represented like in this matrix form. Yeah, that's so these two are equivalent. I could represent in this matrix form. That's the vector. That's the vector. It's just two way of writing the same thing. This is like my parameters here, and this is my unit vector, like pointing to the direction. So I have A. So basically, what does this mean? So I mean I have like this. I like, let's say I want to reach to this point. Like, how could I reach to this point C? So I have to walk a distance A in the I direction. Then I have to walk a distance B in the J direction. And then I have to go up a distance C in the K direction. And that would be like this vector here. Yeah. So that's like a vector A, B, C in the I, J, K direction. I could express it in this way. If I want to find like the magnitude of this vector, you can use Pythagorean theorem. Yeah, that's like how to find like the magnitude of this vector. Okay, so gradient. What is gradient? So gradient. So that is like not a scalar function. That's a vector function. So that's like gradient. So that's a vector function. So I can express like my partial derivative in the I direction, my partial derivative in the J direction, and my partial derivative in the K direction. I could also write it in this way. So these two are equivalent. Yeah, like you see this gradient. It's a vector. You can write it this way, or I can write it in uh, in this way. Yeah. So that's the gradient. It's 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 a vector, and this is like my function. So the direction is the quantity is increasing or decreasing the fastest, and its magnitude at the point. So basically, what is this gradient telling me? It is telling me the direction the quantity is increasing or decreasing the fastest, and then it can tell me like the magnitude and the direction of this like increase or decrease at the point. Okay. So here what we got like we have like a scalar function, like this my function, like this is a scalar, so that's my function, whatever that is. That could be like hydraulic heads, that could be concentration of certain contaminants, that could be the temperature. Yeah. So like, but that's a scalar function. So I have a scalar function, and the gradient, like, so I get like if I took a gradient of a scalar function, what do I get? I get like a vector function. Yeah. So that's like, because that's vector, this is a scalar, and then I got a vector function. So here I have like this vector function, and what this function is telling me, the direction, the quantity is increasing and decreasing the fastest, and the magnitude as the point. And that's why we do this for optimization, because in optimization, that's exactly what you want to know. You want to know like the increase and decrease of your function so that you can find the fastest increase at like a point and the magnitude of this function. The divergence, so like you have like the divergence. So in the divergence, like here, you have like the divergence, like the divergence is like similar, like we put like this. Uh, this is not delta. This is called like a lump uh, Nopla operator. Like so, this like inverted triangles. That's not delta. Like delta is like this. Oops. What did I do here? Just jump into something else. I don't know. Just get back. Sorry about this. Just get back, get back, get back, get back, get back. I don't know. Okay, so see delta is something like this. This guy is called like nop. I don't know. I don't know. It's a P or a P. Like this is like called delta. This is called like Nopla operator. Yeah. So that is yeah. mm, Yeah, Nopla operator. Yeah, that's called like this is yeah. This is delta, and this is Nopla Nopla operator. That's called like the Nopla operator. Yeah. Uh, so here, like the diversion. So now I have a vector function, and so that's like so. This is a vector function, and the diversion. So like I have the gradient of a vector function. So this is vector and this is vector, and the dot product of two vector function, like you end up with a scalar. Yeah. And so and that will tell you about source and sink quality at a point. So like pumping, for example, or injection. Yeah. So pumping, that would be like a sink. Injection, that would be a source, for example. Yeah. And then finally you have the curl, and the curl. So that tells you about like increase and decrease in your function. That tells you about sources and sinks. And this tells you about like curl, like rotation in your vector field. So here we have the gradient. Here's dot product with your function. Here is like cross product with your function. So like here, that's a vector. Your function is a vector. And then when you do like this cross product, and then like you also get a vector. And this will tell you like rotation of the quantity at a point. So we did like some practice problems. So the practice problem are easy. Like you can just like try to look at this. I'm not going to go through the details like in order not to make this long, but I mean you can easily like look at this example and try to solve this problem. So that's like for practice for gradient, that's practice for diversion of a vector field, and so basically like you evaluate like these derivative, and then you can evaluate it at a point. If it is like larger than zero, this means like source indicating region where air is spreading out, for example, source versus negative divergence existing airs as converging in like sink. Yeah, something like this. Okay. And you can find more practice problem in the slides and the video. So here there's also some example of some practice problem you can do. But in the exam, you will also get this conceptual problem. So for example, in vector calculus, the curl of a vector field is a vector that describes the rotation at each point in the field. Yes. A scalar representing the magnitude uh, of rotation of vector field at a point. No, it's not a scalar, it's a vector. A vector that point to the direction of the axis of rotation. with magnitude indicating the strength of the rotation. Yes, that's exactly what it is. It's a vector pointing to the direction uh, of axis rotation with the magnitude indicating the strength of the rotation. So this is true. This is true. Scalars that indicate the divergence vector of the field at the point. This is false because it's not a scalar, it's a vector. So again, even if you don't know like this definition, you can just eliminate, like you can say like this is wrong, this is wrong. So probably these are two are true. And then you look here, this only no, and like probably like these two. Yeah. And this is I got this from FE exam questions. Yeah. So again, like if you can check, if you have an FE exam book, you can check it for these types of questions. And if you want to practice more, but you don't even need to do this because I collected so many of these questions for you in your slides. So go back to the slides, go back to the video if you don't understand it, like you will see the details of this type of thing. Yeah. And and one more thing we did, which is like Taylor series or just series in general, because there are like many series like Taylor series, Laplace series, whatever. But Taylor series particularly, you use this series to approximate a function, and we later saw how this approximation of a function can be very useful for finding an analytical solution, like infinite series solution, because sometimes we cannot get a closed form solution. In terms of like a finite like algebraic equation, and we need to get like this infinite like series solution. Yeah. And that's how Taylor series is important. We also saw why Taylor series are important, because for numerical solution, like when we did the modeling, we seen how like we have a differential equation, we cannot solve it analytically, or we can solve it analytically. We can either can or cannot solve it analytically. But in order to solve it numerically, you do like Taylor series expansions. Yeah. So you do like your function, its first derivative, its second derivative, and so on and so forth. Yeah. And we've seen that like for Taylor series, like you, so I can expand like a function around the point with the step size, like so you define the step size and then like you find your Taylor series expansion. So I have a function, yeah, and I want to know like this function xi plus 1. That's equal to what? That's equal to the function at xi. So this is like the new value, the new x value. That's equal to the previous step, like the previous value times the first derivative at the previous value, uh, and this is and the second derivative plus the second derivative as the previous value. This is h here. That is your step size. That's the difference between xi plus 1 and xi. And remember, like the smaller the step size, the more accurate this approximation will be, and the more terms like expansion term you take, the more accurate the solution will be. So basically the clues accuracy depend on the, so if I have like, for example, like if the function is up like a fourth order function, if I need to take like a fourth order Taylor series term, then I will get the exact solution. Yeah. uh, but if I'm taking like less Taylor series, like let's say I have function like fourth order, I'm only taking like 2 or 3 Taylor series terms, and like the smaller the step size, the more accurate the solution will be. Yeah. So where R is uncalculated remainder after n derivative, which is the difference between the exact and approximate value triangulation error. Yeah. So if my number of series is equal to the order of my function, I will not have a triangulation error. Yeah. But we've seen also like how to do this. So this is like an example. Again, I'm not going to go through these examples again in order not to keep this video long. It's already like getting to 40 minutes. So you can look at these example, like if you cannot solve like an example like this, check back like the original video, check the lecture note, and you should be able to solve like these types of example. If still unclear, please stop by my office and I can help you. Yeah. So I think that's all for this part, and like see